streaming, since we're talking about stuff, I've got just the homework up on my screen. By the way, I don't have anything else of notes to show you yet. Any other questions on homework 3? Okay. Well, if you come up with any, let me know. Office hours at 3:15. Since we have the waiting room thing, I'll just like let everyone in, and then you guys can take turns talking to me about whatever, and you can come and go as you need to. I'm not yet sharing my screen because I don't have anything to share yet. If you need to set an appointment with me at a different time, just let me know, and I can work on that. All right, Crystal. He says, never say famous last words because they could be. I'm not sure which movie that was. It might have been When Harry Met Sally, but I could be wrong on that score. All right, well, we will attempt to share screen. Yeah, I froze for a while. It's because I jinxed myself. That's why. But we're going to try it, and we'll do what we can. So I've got a screen share. What I have up today is Lecture 4 and Example 4. I know that we did the first part of Lecture 4 before, but I'd like to go back over it, if that's okay with you guys. Yeah, rather than just assuming you remember everything from before perfectly? Yeah, okay. So this is Lecture 4. We're moving from models that just have one predictor at a time to models that have more than one predictor. And so special cases when you have a categorical predictor with more than 2 groups, 2 categories, and when you have nonlinear effects of quantitative predictors. So those are specific examples there. All right. So we're talking about general linear models, models where we are predicting a quantitative outcome in the form that is slope times variable plus slope times variable, where the slopes are constants in that they are the same number for everyone that the sample is being shared. We're saying that the residuals are supposed to be normally distributed. It's the residuals, not the original outcome. And these were the models that we talked about before in the review that we had, as well as in lecture and example 3. Empty model is your baseline. That has no predictors. So the role of the empty model is just to spit back the descriptive information about your outcome. The mean is the fixed intercept, and the variance of the E residuals is all the variance that there is to be had in that outcome. So all the reasons why people have different outcome values are up for grabs. In adding a predictor, then, we pick up one more fixed effect. We have a slope. So fixed effects in general are indicated by the betas. An intercept is one kind of fixed effect. A slope is another kind. A slope describes an association of a predictor variable to an outcome variable. We have y hat here as the abbreviation for what each person's outcome is predicted to be. So it's beta 0 as the intercept plus beta 1 the slope for the effect of x. And so anybody who has the same value for x, the predictor, is going to have the same predicted outcome, y hat, for that person. And just to review the terminology, intercept is always the expected outcome when your predictors are 0. That's why it's helpful to have 0 be a meaningful value. All right. Slope. I'll just pause at the end of each sentence. Trick the internet. The slope is the change in the outcome, y, for a 1-unit change in the predictor, x. So a unit, hey Siri, can you repeat? Nice. I'm not a Siri person. I'm not an Apple person. That's my husband. He keeps telling me to come to the dark side and get Apple everything, and I just refuse. So the dark side. Yes. Or as my son calls him, Dark Vader. He started watching Star Wars. And I thought, well, that actually makes a lot more sense if you think about it. Yes, Dark Vader. Slopes, that's what I was talking about. Change in y for unit change in x. And so that is a shifting along a quantitative variable or the difference of the 0 group and the 1 group. So 0 as the reference point, the one group then picks up the slope. In this case, once we have a predictor, or more than one predictor, if the predictor matters in relation to the outcome, if there is an association there, then each person's E, the residual for the difference between what the model says their outcome should be and what it actually is, each person's E should be smaller after accounting for the predictor. And so what we hope is that the variance of the E's across persons, that's what's known as residual variance. It's a sigma squared is the notation there for that, sub E. We hope that that number, residual variance, is smaller, meaning we have accounted for some of the reasons why people had different outcome variables, but there's some reasons that remain. And so residual variance quantifies how much information is still left for us to figure out in terms of why some people have different outcomes from each other. Okay. Good so far? Internet's still working? Fingers crossed? Okay. All right. So in characterizing a slope, you're going to have an unstandardized estimate. So that describes how x and y are related in the units of those variables. So per please and number of fits thrown per please heard, or number of pleases heard for 3-year-olds versus 4-year-olds. The units are part of the slope. Standard error tells us how variable that slope is expected to be across samples. So there's a homework question about that, several in fact. The standard error for the slope tells you the average distance of the slope from the population slope across samples. It's the same concept as a standard error for a mean, but it's a standard error for a slope instead. The standard error is the denominator in what becomes a t-test statistic. So as we talked about last time, t is a function of the size of the effect and sample size, because it's been put onto the t scale. It's not in units of x or units of y anymore. It's on its own metric. And we know based on the sample size, how many predictors are in the model, and our alpha level, what the critical t is supposed to be to declare something significant, and the t-test statistic we get is compared to that. If it is more extreme than the critical value, meaning greater for a positive number or smaller for a negative number, then we declare the slope to be significantly different than 0. It would be unexpected. Less than 5% of the time we would see a slope that extreme if the true population slope were 0. And so once we get our t-test statistic, that gives us the p-value, which is the exact probability of observing a t that extreme if the slope were truly 0, if the null hypothesis were true. Because the slope is in units of y per units of x, we want to make sure that we can characterize it with an effect size that's unitless. That helps us convey the absolute size of the relationship. And when you only have one predictor in the model, that effect size is the Pearson correlation. You can standardize the slope, and that's what it becomes. So this formula works for any model that has more than one predictor as well. You have the unstandardized slope multiplied by the standard deviation of the predictor x, and then divided by the standard deviation of the outcome y. That gives you a standardized slope, which ranges from -1 to 1, tells you the strength of the effect, where a negative slope means as x goes up, y goes down. A positive slope, as x goes up, y goes up also. Okay. Any of that you need me to say again? Or are we good? Good? Okay. Got a couple of thumbs. All right. So in characterizing a binary predictor, So this is, for instance, age group in homework 3. If we have group as our predictor variable, the mean for the 0 group is given directly by the intercept, because that is when this linear model, the slope for it drops out if it's the 0 group. To get to what the mean is for the 1 group, it's the intercept plus the effect of the slope. And so this quantity that's given by the intercept plus the slope, beta 0 plus beta 1, that's a linear combination. And you can get that quantity as well as its standard error using an estimate statement in SAS or a LinCom statement in Stata. And page 6 of example 3 has the code for that if you need to have a reference for that in working on your homework. But the key thing here is that if there's only 2 groups to be compared, if your predictor has 2 groups, then you only need 1 slope to differentiate them. There's only 1 possible difference between 2 groups. However, if you have more than 2 groups, you need more than 1 slope. So if I have 3 groups, then I need an intercept and 2 slopes. That's 3 fixed effects that will perfectly recreate my 3 means. If I have 4 categories or groups, I use those terms synonymously. If I have 4 groups, then I need an intercept and 3 slopes, and that's 4 parameters that will perfectly recreate my 4 means. So in general, the number of slopes that you need is always 1 fewer than the number of groups that you're trying to include as a predictor. And this idea of looking at whether groups differ in their outcome means is known as analysis of variance, or ANOVA as an acronym. One new message. Do I have a cheat sheet for Stata commands? Yes, although it's very long. On the website for my book, Piles of Variance, I have a program guide for each of the programs that's featured on there, and it has examples of all kinds of things. I think there's a link to that on the course webpage in one of the top boxes. Repeat what I said about the analysis of variance. Sure. More generally, if you want to know whether the means of a quantitative outcome differ across groups as your predictor, and it's more than 2 groups, that's known as analysis of variance, or ANOVA. The means of a quantitative outcome. For example, like on the next slide here. The means of a quantitative outcome across groups as a predictor. Yes. So using the general social science data set, we have personal income now as our outcome variable to try and give this a little bit of concreteness. So personal income, and the predictor that I'm looking at here was a question in the data set as to what income class you felt you belonged to. And so there are 3 categories represented here. There's lower class or working class as one, middle class or upper class. And so you would expect that a person's self-reported class would align with their income. People who make more money probably would declare themselves upper class. So this would be one variable that's group. What class are you in? And there's 3 possible categories. The outcome is personal income, so money again. So we have the mean personal income across these 3 groups is what we're looking at. That's an analysis of variance. Because I have 3 groups, I have to put in 2 slopes that's going to differentiate them. So that means creating new predictor variables. And so you've got a little bit of practice with this in homework 3. I asked you to make 2 new variables. You had to center each of your quantitative predictors at a particular constant. You'll get a lot more practice with this in the next homework, making new variables to be able to include as predictors in your analysis. The first part of homework 4 is doing something along these lines, but it's with 4 groups instead of 3. So you have to decide who your reference group is going to be for your categorical predictor. There's no wrong choice for that. I picked the low group because it's the lowest and it had the most people. That's a common strategy. So what that means is that in the slopes I'm creating, the definition of who is the reference group is the group that's coded 0 for both. So the intercept of the model will then be the predicted mean for that reference group, because the intercept is when the predictors are equal to 0. We're setting it up so the predictors are equal to 0 when I'm at my reference group here. So the low group is my reference group. This first column here, L versus M, that's the name that I'm giving to the new column in the data set that I would be making. And I'll show you the code that does this after we talk about this conceptually. So this predictor is designed to capture the difference between the low group and the middle group. So the low group is 0, the middle group is 1. The upper group is also 0. And if all we put in the model was just this first column, then it wouldn't actually separate low from medium. It would lump together low and upper and separate that from the middle group. So to be able to distinguish the low and upper, I need another variable. And then this variable, low is still 0 because it's the reference group for the model. Middle is also 0 because this variable does not pertain to it. And upper is 1 because the job of this variable is to distinguish low from upper. That's what it's for. So when you put them both together, it works out that each does what it's supposed to. The first variable, L versus M, captures the mean difference of going from the low group to the middle group. The second variable, L versus U, captures the mean difference in going from the low group to the upper group. And so the equation would look like this. I've got my intercept beta 0. That's the mean for the low group. Beta 1 is going to give me the mean difference of the middle group relative to low. And beta 2 is going to give me the mean difference of the upper group relative to low. Okay, with me so far? Yeah. So actual, the difference is in what y means versus y hat. Y sub I is the y outcome variable where each person has a different value. That's what the sub I means. It's what's actually in the data set. It's the observed outcome variable. So that includes the model that we're using to predict it, and it all. Y sub I is the outcome for person I. It's a variable that exists in your data set. So it's a variable, not a constant, which is the sub I part, is used to indicate that. So we're saying that a person's outcome Y is going to be predicted by which group they're in, but we expect that just knowing which group you're in is not enough, because there are going to be differences in the outcome among people from the same group still. To reflect that, we also include in the model this E. The E residual is then the remaining difference between what the model says your outcome is going to be and what it actually is. So the Y hat in the next line does not have E because what Y hat means is predicted. Y hat, sure. Y hat means it's the predicted response for person I. Y hat is an abbreviation that contains all the model information with respect to the predictors and the intercept. Y hat is an abbreviation for what the model says that Y should be. So these three terms here, beta 0, beta 1 times the variable plus beta 2 times the variable, Y hat is an abbreviation for that set of three things. Yes, for the linear combination, the result of adding all that together, that result is Y hat. So it's an abbreviation for how each person is supposed to get their own predicted outcome from the model. And so because it's a prediction, it doesn't have an E. The predicted part plus the E for the unpredicted part, that's what gets you all the way back to regular Y, the original outcome variable. Y with a sub I, sorry, I should, yeah, Y always has a sub I. Likewise, the L versus M, that's the name of the new predictor column that we would be making. It gets a sub I, and L versus U gets a sub I because those are individually varying things. For each person, it would be whichever value that variable was assigned based on your group. And yes, John Paul, it does sound simple until you have to code it. But lucky for you, I have lots of examples for you, and you can practice. So in this model, there are three groups. We're trying to distinguish the means between the three groups. So far, how the upper group is. But we still would want to know about middle versus upper, right? Well, we don't have to do anything extra in terms of adding that to get to the model to tell us. It's in there as a linear combination. So if we look at the bottom here, linear combinations of model parameters here, the model tells us how to get the mean for any of the three groups. The middle group mean is the intercept plus beta 1 for how the middle group differs from the low group. Beta 2 is not involved because the middle group is coded 0 for that, that coefficient. Here I am. For the upper mean, it's the intercept beta 0, not including beta 1. That drops out because upper is 0 for that term, but it does pick up beta mean is beta 0 plus beta 1. So therefore, the model tells us, too, how the middle and upper groups differ. And that's beta 2 minus beta 1. So we just have to know how to ask for that missing contrast because it's implied by the model even if none of the model slopes gives it to us directly. We lost you for 30 seconds. Nah! I love online instruction. This is so awesome. Okay. Am I back? I'm back. Okay. Where did you lose me? I am better at it than most. I am less shitty than other people. Yay me. After the middle mean. Yes. We're going to try. We're going to get through this one way or the other. Middle mean. Yes. Okay. So the middle mean is beta 0 plus beta 1. The model tells us that. The model tells us that the upper mean is beta 0 plus beta 2. Well, if I take the mean for the upper and subtract the mean for the middle, the beta zeros cancel, and you get beta 0 minus beta 1 as how the model tells us that the upper group differs from the middle group. So every time that you have to add a slope because there's more than one group, then there's more than one model implied result of that slope. So if I had, say, 4 groups instead, like you're going to get a chance to practice in your homework. If I have 4 groups, how many slopes do I need in my model to differentiate my 4 groups? Yes, you can hold up your fingers or you can type. If I have 4 groups, how many slopes do I need? Yes, 3. Very good. Now, how many possible mean differences are there among 4 groups? How many pairwise? I've got 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. There's only 6. But more than 4, though, right? For sure, yeah. And if we did it for 5 groups, I believe there are 10. If I had to do that, I'm sure there's like a rule that I learned in like 6th grade math, and it's gone as to how I could figure this out. But I know for 4 groups it's 6. But I only have 3 slopes. But that's all I need. Those 3 slopes in linear combinations with each other combine to give me all 6 possible differences. It's cool, according to me. But I'm a giant nerd, so yes, binary comparisons. Pairwise is what it's called when you're comparing one group to another group directly. Yep. Okay. 3 groups. If there are 3 groups, there are 3 possible group differences. 2 are given by the model as the slopes, and the third is a linear combination of those 2 slopes. That's what slide 5 here is showing, how that works. Yes. Yes. In this case, there's only 3 possible pairwise mean differences among 3 groups. The model gives us 2 of those directly as the slopes, and the third as a linear combination of the slopes. If I had 4 groups, that is 6 possible pairwise mean differences. But I only need 3 slopes. Those 3 slopes will give me 3 of the 6 possible differences directly, and the other 3 are linear combinations of those slopes. Okay. Does that make sense? Okay. All right. Let's see, what's next? Oh, code. See? Because understanding the logic doesn't do you any good unless you can make the computer do your logic, right? 1 intercept and then a slope for each of the other groups. It's 1 intercept and then a slope for how each group differs from the reference group. So if I had a 4-group situation, I'd have the intercept is for my reference group. And then each other slope then would be for an alternative group relative to the reference group. There we go. I'm muting John Paul. He's dealing with a crisis of some kind here. Yeah, I heard that several of you have a construction going on or other sorts of noisy disruptions. That's super fun. Yeah, I'm in my basement, which is actually really quiet. So I'm very lucky in that regard. It's a walkout basement. It's not quite as depressing as it sounds. So I'm looking around like, yeah, I'm in my basement. Okay. So code, then. So the logic of what the code is trying to do is on the top of the slide 6 here. And then how the code accomplishes it is on the bottom here. So I would have already made this low versus medium and low versus upper variables. And so they go into the model as my predictors. And these estimate statements, in general, you use those to make SAS do math for you. That's what they're for. The words in these statements actually refer to the name of the variable that you want the fixed effect for. So when you see the word intercept, for instance, that is you telling SAS, hey, whatever you thought the intercept was supposed to be, the estimate that you found for my intercept beta 0, go take that number and stick it in this equation for me. So the word intercept is a placeholder for what the estimate for the intercept is going to be when it's done finding the results for you. The 1 after it tells you how many of those you would like to include in your linear combination. I only need 1 intercept ever. So intercept 1 is the starting point for how each of these lines is going to give us what the mean is for each group. L versus M, that is referring to what the slope for that predictor variable, what that slope's estimate is going to be. So it's beta 1 is what L versus M means here. The value that goes after it is in your data set for somebody from that group, what is their value on that predictor. If I'm in the low group, let me go back. The low group is coded 0 on that variable. The low group is coded 0 on the other variable as well. And so I don't actually need those slopes in creating a mean for the low group. So this line is redundant with what you'll actually get already. It's the fixed intercept, but I'm including it for pedagogical reasons. Okay, with me? Okay, that must mean the internet's happy with me right now because you all nodded quickly. Okay, good. Middle group. Intercept, we need one of those. If you're in the middle group, your value on this low versus medium predictor is 1. So we do need 1 beta 1 in predicting your outcome. If you're in the middle group, your value on this lower versus upper predictor is 0, so we don't need that one. So this middle line, what that is beta 0 plus beta 1 when all is said and done. The upper group, I need an intercept. If I'm in the upper group, I'm coded 0 for the first predictor here, and I'm coded 1 for the second. And so that gives me beta 0 plus beta 2. So these second and third lines, the means for the alternative group is the way that I'm phrasing that. The low group is the reference. The low group is who the intercept is for, because the low group is where all the predictors are coded 0. These other groups are the alternative groups. Their means would not be provided for you on your output unless you asked for them. And so I'm showing you how to ask for that extra information. The next 3 statements describe how to get mean differences. So if you go up to the first part of here and look at the logic, it's what does the model say the mean for each group is going to be, and if I want their difference, then I subtract one mean from the other. So the middle group mean is beta 0 plus beta 1. The mean for the low group is just beta 0. If I subtract beta 0 from beta 0 plus beta 1, all that's left is beta 1. Likewise, if I have low versus upper, all that's left is beta 2. And it's the third one that is the linear combination of betas that we're not going to get directly from the model. The mean for the upper group is beta 0 plus beta 2. The mean for the lower group, or excuse me, the middle group is beta 0 plus beta 1. If I subtract the mean for the middle group from the mean from the upper group, the beta zeros drop, and I've got beta 2 minus beta 1 as how the alternative groups differ from each other. So this example has 3 groups. There's 3 possible mean differences. my model has two slopes. Those two slopes directly cover two of the three mean differences, and the third mean difference among the alternative groups is a linear combination of those two slopes. And it's down here in the last line that I get that slope difference linear combination that tells me how the middle and upper groups differ. Okay. Any of that you want to hear or see again? No? Okay. Stata people, exactly the same. Your commands are called lincom. The only difference is that you use equations that look like equations here. So you have an asterisk to indicate that the variable's fixed effect is going to be multiplied by that constant, whereas in SAS before there was no asterisk for the multiplication, it was implied. And the fact that you're adding these things together is explicit with the plus signs. But otherwise, the logic and what this is doing is exactly the same. It doesn't allow you to put a title on there, and so the / with the green here, these are comments that I made to try and indicate what the result of this statement is supposed to tell you. So what we're going to see in our example, these are the results. To remind you, these are the two variables that we have up here. From an empty model, for this outcome, it's personal income. An empty model doesn't have any predictors, so this is our baseline. Everybody is supposed to have the mean as their predicted outcome. That's the worst we can do. And all of the variance in the outcome is still there because E is just the difference between the mean and your outcome value, excuse me. And so 190.2, that's all the variance in this outcome that there is to be had. All the reasons why some people make more money than each other. On average, people make $17,000. Now, after putting in class, so 3 groups, 2 slopes to differentiate the 3 groups, here are the estimates. So beta 0 is my fixed intercept. Beta 0, fixed intercept, always, always the expected outcome when the predictors are 0. In this context, it's the predicted money earned when your predictors are 0, and that happens when you're talking about the low group. So 13, the estimate for beta 0, is the mean for the low group. Beta 1 tells us how the middle group differs from the low group. That slope coefficient is 8, so the middle group makes $8,000 more than the low group on average. The standard error for that is 1. That creates a t-value of 8 as well, and that's a p-value that's very significant. It's less than 0.1% of the time you would see a slope that big if the true slope were 0. Unexpected. Beta 2 tells us how the upper group differs from the lower group. The estimate is about 11. 11 divided by the standard error of 3 is a little under 4, also a significant result. So the upper group on average makes $11,000 more than the lower group. If I wanted to get exactly what the predicted means are for the middle group and the upper group, it's beta 0 plus whichever slope differentiates their score from the low group. And then the model implied difference, 10 minus 8 is given, here's the 2. With the standard error of 3, though, that's a t that's less than 1, and a p-value of 0.48. So this is a non-significant comparison. 8 and 10 are basically the same. There's not enough evidence to say that the difference between 8 and 10 is different than 0. You would get a difference that big 48% of the time, highly within expected territory. Okay. 22.5. Which number are you looking at? Oh, this. Yes, my giant pink mouse. Oh, 2.1? 22.5. I'll say, I don't have a big black mouse. I made it big and pink so I would stop losing it. Yes. Ah. 22.5 is what the model says the middle group is expected to make. Yes. Yes. Yep. And followed by the same logic, the upper group, that's a typo. Looking at this, 13 plus 8 plus 10 is not 24. I'll have to fix that. But yeah, I need to fix that number. But the difference between middle and upper is, no it is. No, that's right. I'm losing my mind. No, it is 24. Okay. It is actually, this is the General Social Survey from 2012. Yeah. Well, they got to pick what they consider themselves to be. Mhm. Yep. Okay, Jen, are you back? I just saw your note. You're back. Okay, yeah, it looked like you were there. I just want to make sure. Okay. Yep. Yes. So, point being, the model tells us what the three means are. The model tells us how each of the means compares to the other. That's what it's doing. Whether each mean is significantly different from each other. That would be the reason to do this analysis. So at the same time that we would want to know how each group compares to each other group, we also want to know whether group matters in a more general sense. So the idea is we want to know, like, to put the slopes back together again, to say, okay, does this model significantly predict my outcome variable? That's a more general question. There's lots of examples of this, but anytime you want to lump the effects of predictors together to ask if their joint result is significant, if we've predicted the outcome variable more than chance, that's what we're talking about here, is a general concept. So we can phrase this general concept in two different ways. If group matters, if these slopes work together to create group differences, then the residual variance, the variance of the e's, should be smaller than what it was to start with. So let's look at that in this example here. So from the empty model, 190 is all the variance that there is to be had in this outcome variable. After putting in group, the variance of the e's is 171. So each person's e, each person's residual for how far off their real outcome is, y sub I, from the one that's predicted for them by the model, y hat sub I. That difference should get smaller and smaller the better the model does in creating each person's predicted outcome. So 190 versus 171. Well, 171 is clearly lower, but is it significantly lower? Meh. That's what I want to know. The other way to think about this is in relation of y with y hat. Original outcome with the one that's predicted for each person. If the model's any good, the predicted outcome should be related to the real one. So we want to test as to whether or not the predicted outcome y hat is related to the original. So that's the same test. These are just two different ways of explaining it. Is the variability lower because of the model? And is the predicted outcome correlated with the real one? Does the model work, so to speak? And at this point, what's in the model is just group. So does group matter? Do the two slopes work together to explain residual variance to create a significantly correlated predicted outcome? This concept of lumping slopes together to answer that type of question is what's known as a multivariate wall test. It requires a new test statistic, f, which is in squared terms. So the way that f is constructed here, working backwards, is we have to find a way to quantify how much information the model has picked up and how much information is yet to be explained that we don't know why. So, sure, to figure out if this model works, if it significantly predicts an outcome, if the slopes work together to do something useful, we have to know how much information has been captured by the model relative to how much information is still left out there up for grabs. Now, each of those needs to be qualified by what it took to get that information. How many slopes did it take to get to the level of prediction that you did? It's more impressive if there's fewer. So the idea of how many slopes did it take, that's known more generally as numerator degrees of freedom. So it's the number of fixed effects in the model, not including the intercept, because the intercept is already in the empty model. So if I go back to compare these two models, the empty model has beta 0. The model that has group in it also has beta 0. The question is, how many more terms did I have to add? And it's the number of slopes that tells me that. That's numerator degrees of freedom. So how much information did the model get? And I'm using the term information because I don't want you to confuse it with variance, because information is the numerator of variance. It's this term called sums of squares. So all of the information that's available in an outcome variable is the information is what's given by the empty model. So y sub I minus y bar, that's how far off each person's outcome is from the sample mean. That's all the information. Okay, that's sums of squares total. Now we're talking about carving that up into what is known by the model versus not yet known. So known by the model means, okay, best naive guess for everybody was just the mean. By adding predictors, I'm going to customize that predicted outcome for each person based on their predictor values. So in this context, it would be each person's predicted outcome would be one of three numbers, right? The low group, the middle group, the upper group, as opposed to just the one. So sums of squares for the model, the way that information is operationalized, is the difference between what your model says your outcome is going to be, y hat, minus the mean, which is what the empty model said it was going to be, your best naive guess. And so, Dre, going back to your question a while ago, what is y hat for? Y hat is an abbreviation. It makes it easier to look at this and understand what it means, because y hat is always, what does the model say? What the model has in it can change, but what the model says the predicted outcome is y hat. So this is how far off your predicted outcome is from your new model versus a naive guess that's the same for everybody, which is the mean. So how much information have you introduced into your predicted outcome? Relative to how many slopes did it take for you to do that? So information obtained by the model relative to slopes that it took, that's mean square model is what that's called. And this shows up on your output. The other half of this, what's left? How much information is still up for grabs that we don't know yet? That's sums of squares residual. And it's how that information is operationalized as how far off your real outcome is, y sub I, minus the one that's predicted by the model, y hat. So how much further do we have to go? I gave you your model predicted outcome. Now let's compare it to the real one and see how far off you are. Those offnesses, that's sums of squares. When you square it so that the negatives and the positives don't cancel, sum it across the people. So there's a lot of information up for grabs. You want to then scale that relative to, well, how many more slopes do you have that you could actually put in this model? And that has to do with how many people you have. That's denominator degrees of freedom. And it's the number of people minus the number of fixed effects. And so if you take information unknown, sums of squares, all the differences between what the model says you should have and what you really have, divide that by the number of slopes remaining, that thing is mean square error or mean square residual. Those terms are synonyms. That's your residual variance. So in talking about example 3, I told you where the residual variance was in the output, right? There's a table, and it's like sums of squares and mean squares, and then there's degrees of freedom, and there's a coordinate system, and then I was like, look at that number, that one's residual variance. And I said, we'll talk about the rest of this later. This is the point where we talk about the rest of it. So here's the table that you'll get on your squares model. How much information is captured? Let me guess. My Zoom is cracking out again, isn't it? Yeah. See, it's funny because I get the message that says your internet is unstable. At the same time, I see your faces go, like, oh. Okay. Are we back? Back again? Okay. All right. So information, that's what we're talking about here. How much information is captured by your model relative to what's left over? Start from page turn. Okay, I'll go back. Wrong way. Okay, this is where we were. So mean square model, that idea is how much information has your model captured in your outcome relative to how many slopes it took. That's one thing. Now, how much is left? How much is left over is unexplained relative to how many slopes you could put in but you didn't. Info explained over info unknown. That forms a new test statistic that's known as F. So the worst F should be theoretically is 1, meaning you know as much as you don't know. Since everything is in squared terms, F is positive. F looks like this. It looks like chi-square. F and chi-square are the same type of distribution, except that F also has denominator degrees of freedom, whereas chi-square does not. But they're both squared, so they never have negative numbers. So there's 2 different ways you can think of F at the bottom of slide 12. The way that I just explained it to you, information known over information unknown. That's mean square model over mean square residual. That's one way to get F. The other is to phrase it in terms of R square, where R square is the proportion of information captured by your model. It's sums of squares total, all the information in the outcome that there is to be had, minus how much you didn't get, how much is left over divided by total. So R square is a way to quantify what proportion of the variability in your outcome has been captured by the model. Where you got nothing, that's 0. You got everything, that's 1. Somewhere between 0 and 1. It can't go negative because it's in squared terms. So the significance of R square, the significance of how much information has been captured by the model, that's given by an F-test. All right. How are we doing? Yeah? Okay. Any of that you want to hear again? Theoretically. No, F goes from 0 to infinity. R square goes between 0 and 1. It is, what a 1 means is that if you go all the way down to 0, that means that you actually you did worse than chance in terms of your model. That's not likely, although it is theoretically possible. But the highest value of F you can have is infinity. What a significant F means, how you figure out what the critical value is, depends on how many slopes are in your model and how many slopes are left over that you could have put in your model. Denominator degrees of freedom is the latter. And so F changes its shape based on those two things. So for instance, in slide 13 here, the shorter hump is if you had 8 slopes in your model but 4 were left over, whereas 8 slopes in your model but 40 left over. They're different shapes. You don't need to know what the expected F shape looks like ever. All you need to know is what your F test tells you and the p-value that goes with it. That's set by your software. But where the p-value comes from is comparing your F to this theoretical distribution. Yep. Yep. Yes. And how many people? Yep. Yep. So everything that you've learned about significance testing so far still holds. This is just another kind. So we did, significance of what is my sample mean versus my population mean. We did that with a T. We have a proportion of 1 values versus a population proportion of 1 values. We did that with a Z. For a slope, is my slope estimate significantly different than 0? We do that with a T. This is, are my set of slopes for my model, is that significantly different than 0? Is the R square, is the variance accounted for by my model significantly greater than 0? That's an F, and we get a p-value that goes with that. So anytime you're lumping together more than 1 slope, that's called a multivariate wall test, and it uses an F distribution if you're paying attention to sample size, which you should be. Okay. So the reason why you haven't heard about this up to this point, even though we've been talking about models for a while now, is because if you only have 1 slope in your model, the test of that slope is the same thing as the test of the model. So this is a homework question for homework 3 for those of you who are still working on that. If you have 1 slope in your model is the slope. So the t-value for that slope squared is the same thing as the F value for your model. There's a one-to-one correspondence. So if your slope is significant, your model is significant. If your model is significant, that means that you significantly explained residual variance. It went down significantly after you put your slope in the model. So now we're talking about a distinction between what a slope is and what a model is. If you have more than one slope, your model is the set of slopes together, and that can be significant or non-significant. Each slope individually can be significant or non-significant. All right, so here's the table for the model in this example. F is always going to be over here. So in the handouts that for example 4, I tried to bold the numbers that would show up in a report. In reporting these things, there is a universally accepted format that's right here. You need to tell people about your model the following things. Your R-square, what proportion of variability has your model accounted for, where 0 means none at all and 1 means all of it. And then a significance test of that R-square. F is the test statistic. In order to know how to interpret that F, you have to know your numerator degrees of freedom and your denominator degrees of freedom. Numerator degrees of freedom is the number of slopes in your model. Denominator degrees of freedom is the number of slopes that could have been in your model. It's n for your sample size minus a number of fixed effects. Then we have the F value. Next comes the residual variance. And so this is labeled on your output as mean square error or mean square residual. In SAS, it's called mean square error. In Stata, it's called mean square residual. It's the same thing. And then you give them the p-value that goes with the F. The reason why these are the values that get extracted from the table is because with these values, you can recreate everything else inside the table. You give them F, you give them mean square residual. If you know mean square residual and F, you can get back to mean square model. If you know degrees of freedom for each kind, you can get back to sums of squares. And that was one of the things that I had to do in other stats classes is recreate a table like that. But if you give them these pieces of information, anyone can recreate the table if they wanted to. All right, and that's what we'll do. One last aside, there is another version of R-square that Reviewer 3 may ask you to provide someday. Yes, it's actually Reviewer 2. Reviewer 3 is an older convention when people insisted on having 3 reviewers. I'm associate editor for a journal, and I'm only asked to get 2. And it's like pulling teeth to get those. So Reviewer 2 is the new meme. So in case Reviewer 2 ever asks for something called an adjusted R-square, here is the formula for that. You can get that from your software as well. Stata provides it to you with it shown that it's upwardly biased, and so you can report an adjusted R-square instead. I have never been asked for this, but some people swear that this is the only thing you should report and the regular R-square is bullshit. So I'm not going to weigh in on that debate, but I want you to know that it exists, and so you can choose which one to report so long as you tell people which one it is that you've chosen. So for our example, the R-square differed in the 3rd decimal place. So I'm not gonna lose sleep over that. All right, and then effect size. D's. We talked about this before, but I wanted to remind you that we had talked about it. Okay, how are we doing? Okay, so the next piece of this here, I'll lay the groundwork for what's coming since we're out of time. As somebody who is called a statistician, I'm not. My degree is in psychology. Seriously, it is. But one of the things that I get asked to do in helping people write research grants is to do a power analysis. every research granting agency wants you to do a power analysis. And so investigators come to me and they say, I need a power analysis. I'm like, what do you want power for? What do you mean? Well, as we've heard here, each slope has a power associated with it. The model as a whole has a power associated with it. Every linear combination involving slopes has a power associated with it. Now, which one do you want? That's my question. So yes, real stories here. So that's setting up how do you figure out what your power would have been post hoc. I gave you a table by which to do that, and then the next slide talks about what it would be for this example. So that's where we'll pick up next time. So office hours at 3:15 if you want to come back and chat today. Otherwise, have good weekends. Stay safe. Let me know if you need anything. Bye, guys.